Cycloalkanes. There are two types of strains in the rings that make them unstable. The first kind is angle strain. Angle strain happens because a carbon inside a ring is sp3 hybridized, and that means that it wants to have a 109.5-degree angle. So for example, this carbon is connected to two hydrogens and two carbons. It has sp3 hybridization and it wants to have a 109.5 angle. If the angle is not 109.5, that causes a strain that is called angle strain. So let's go ahead and take a look at our rings. Here I have cyclopropane. Cyclopropane has a 60-degree angle, which is very far away from 109.5, so it must be very unstable. Next I have cyclobutane, 90 degrees. Cyclopentane, 108. And cyclohexane is a 120-degree angle. The second type of strain that rings can have is called torsional strain, and that is when hydrogens end up in eclipsed versus staggered conformations. And as we learned before, eclipsed is unstable because basically hydrogens are bumping into one another, and that causes the ring to be unstable. So let's go ahead and see how our rings can solve this problem. Cyclopropane cannot do much, and we can see that not only does it have a bad angle, but it also has hydrogens in eclipse conformation. They're bumping into one another, so this ring must be very unstable. Cyclobutane is next, and what happens is it adopts a slightly puckered conformation to alleviate some of the torsional strain, so that hydrogens are no longer eclipsed and they're staggered. Cyclopentane also twists itself to alleviate some of the torsional strain, and it looks like something like this. The best of all rings though is cyclohexane, and I call it the king. Why is it the king? Because it can adopt a lot of different conformations, but there is one particular one that alleviates both angular and torsional strain and makes it much more stable, and that conformation is called shear. So it's a very important concept in organic chemistry, and we will first learn how to draw shears correctly, and then we will talk more about them and solve problems with them as well. So how do we draw a shear? We start by drawing two lines parallel one another. Then we draw two more lines parallel one another, go overlapping a little bit, and then we close the ring, and this is our shear. A shear can flip, so we can draw another shear which is its flipped version. When a shear flips, this is how we would draw it. We would draw two parallel lines, but they will be parallel in the opposite direction. And then we draw another set of parallel lines overlapping like this, and we close the ring, and this is our flipped shear. So this is our shear conformation and its flipped shear conformation. Next, we have to add the substituents, and it's very important to know all of the positions for the substituents on a shear. So what I do first is I draw all the vertical substituents. I go up, down, up, down, up, and down. And I do the same here, up, down, up, down, up, and down. So these, all of the vertical positions, they're called axial. They're either straight up or straight down. So everything we have drawn here, it's axial. The next set of positions are equatorial, and they're diagonal. So if this is up, this position will be down parallel to this line. So down parallel to this line. This is down, so this must be up parallel to this line. Up parallel to this line. This is up, it has to be down parallel to this line. And this is down, so I have to draw my substituent up parallel to this line. This is up, so it is down parallel to this line. And finally, this is down, so I'm going to draw the substituent up parallel to this line. And it's very important to draw the shear correctly and to draw the equatorial and axial substituents correctly. So again, everything that we have drawn either straight up or straight down is called axial, and the positions that we have drawn that are diagonal, not straight up or straight down, but at an angle, they're called equatorial. We need to know that axial is least stable, is much less stable than equatorial, and equatorial is more stable. So whenever we draw a chair and we asked for the most stable conformation of the chair, we want to draw the chair with the most equatorial positions. I have written here, so you can take it as a guide, everything that is up and down. So each position will have an up and a down position, each carbon, and we already went over it, so this is just a little overview of what we have done so far. For example, this carbon up will be equatorial and down is axial here. On this carbon, up is axial and down is equatorial. And we do the same thing for the flipped chair as well. So let's go ahead and do a little bit of practice. Here we are told that the following is a chair conformation of cyclohexane showing one methyl and one hydrogen. We have to indicate using a label whether each group is equatorial or axial. And next, we will have to draw the alternative chair conformation and again label each as axial or equatorial. So let's go ahead and take a look. What is this position here? You can see that it's straight up, and so it must be axial. This is an axial position. What about this hydrogen? It's not straight up or straight down, it's at an angle, so this position is equatorial. And how would we draw its flipped version? So again, to draw its partner, we will draw two parallel lines. Notice the lines are parallel in this direction, so I'm drawing them the opposite direction. Next, two lines overlapping, then we close, and we're done. Next, what we're going to do is we will number this cyclohexane, this chair 1, 2, 3, 4, 5, 6. And when I number my flipped version, I'm going to start one carbon down. So this is going to be my number 1, 2, 3, 4, 5, and 6. My 1 is up. So where is up on this position? Well, up on this position is this way. It is parallel to this line. So this must be my methyl. And let's go ahead and do hydrogen. Hydrogen is on number 3 and it's down. What is down on number 3? It's straight down. So this is my hydrogen. Is my methyl group equatorial or axial? This is at an angle, so this is equatorial. Equatorial. What about the hydrogen? The hydrogen is straight down, so that must be axial. Let's practice drawing the most stable chair conformation of cis-1,2-dimethyl cyclohexane and trans-1,2-dimethyl cyclohexane. First, I'm going to guide you through how to do it, Maya sip, and then we will go ahead and do it. So we first have to draw cyclohexane with both groups on it, and since means both are either wedge or dash, so either both wedge or you draw both of them dash. And trans means one group will be wedge and another will be on a dash. Let's go ahead and do that for cis-1,2-dimethyl cyclohexane. So I draw my cyclohexane, I number it, and on 1 and 2 I have methyl groups, and because it's cis it means both are wedge or both are dash. It's up to you, but I'm going to choose for both to be wedge, for example. So both methyl groups are wedged. Then I draw the chair, so let's go ahead and draw the chair. And number the carbon on it 1 through 6, where 1 is on the top right. So I go like this. 1, 2, 3, 4, 5, and 6. Next, I have to know that wedge means up and dash means down. So let's go ahead and write this. This is up. So both groups must be up. What is up on carbon number 1? Again, we can double check with our little prototype here, and we can see that it's straight up, and we can also remember how to draw the positions on the chair. But 1 is straight up, so I draw straight up. Straight up. What about 2? 2 is up also. Where is up on 2? It's parallel to this line. So this must be 2. So that must be my chair. Now I have to go ahead and draw the flip chair. So for flip chair, I draw 2 parallel lines again. Another 2 parallel lines overlapping. And I finish my chair. Then it's very important for me to number this as 1. So here, my carbon here was 1. Here is this one. 1, 2, 3, 4, 5, and 6. 1 is up. What is up position on carbon 1 here? It's parallel to this line. So this is my method here. And 2 is up. What is up position on carbon number 2? It's straight up. So these are my 2 chairs. I have to label all substituents as axial or equatorial. So let's go ahead and do that. What is this? It's straight up, so that must be axial. This is at an angle, equatorial. This is straight up, axial. This is at an angle, so it's equatorial. And I'm told that the position with the more equatorial groups or with bigger groups on being equatorial is the most stable and lowest in energy. Let's compare these two chairs. The first chair has 1 methyl axial and 1 methyl equatorial. The second chair has 1 methyl axial and 1 methyl equatorial. So in this case, these 2 chairs are equal in their stability. They both have 1 axial methyl group and 1 equatorial methyl group. So it would not matter. Now, let's draw the 1, 2 trends. 1, 2, 3, 4, 5, 6. And I'm going to choose to put this wedge and this group as dashed. And let's do it again. Let's draw our chair. And we're going to write 1, 2, 3, 4, 5, and 6. 1 is up. What is up on this position? Straight up. 2 is down. What is down on this position? Straight down. So it's a little different from this, as you can see. Remember that wedge is up and dash is down. So this is how we go from the two-dimensional drawing of cyclohexane to the chair. Remember that wedge is up and dash is down. So here we have up and down. Now let's go ahead and draw its flipped version. We draw 2 parallel lines, overlap them, close. We can start numbering here. 1, 2, 3, 4, 5, and 6. 1 is up. What is up position on 1? Where does it go? Again, you can always double check with the prototype that I have written above. But 1 up on this is parallel to this line, so it should go like that. 2 is down. Where is down on 2? It must be parallel to this line, so it's going like this. And now let's label each one as axial or equatorial. This is straight up, so this must be axial. This is straight down, it's axial. This is at an angle, so this must be equatorial. This is at an angle, equatorial. Which one is more stable and lower in energy? The left chair or the right chair? The most stable one is the one with the most equatorial groups. So this chair must be most stable.